dear students, welcome back to my channel. My name is Prachi Sharma and today is another session for the series that is going on for mind mapping. In the previous sessions, we have covered sulfuric acid, nitric acid and hydrochloric acid. Today's session is based upon ammonia. Mind mapping is a consolidated way in a short and crisp video to cover up the whole chapter and give you all the important information that you need for the examination. Make sure that you join the Telegram channel, subscribe to the channel, and also share it with your friends and family and help us move forward. Without wasting any more time, let's get started with ammonia mind mapping. So, my dear students, I hope the screen is clearly visible to you. Let me give you a quick heads up on how this is going to work out. The first screen that you can see here is based upon ammonia lab preparation and everything. A couple of experiments. The next screen that you see, it contains Haber's process, that is industrial manufacturing of ammonia. And then you have a few other reactions and chemical properties for that. And on the last page, I have the lab preparation for dry ammonia that was mentioned on the first screen. So you have two different lab preparations. This is the first one, diagram for the first one. So let's start with the preparation for ammonia. First, you have the general preparation. In general preparation, if you can see on the screen, you have any ammonium salt that is reacting with an alkali. We are taking the examples of slaked lime, caustic soda, caustic potash. That will give you a salt plus water plus ammonia gas. Now let's look at the equation. So NH4Cl, that's a salt of ammonia, reacting with slaked lime, giving you CaCl2 plus water, and along with that ammonia comes out. Same thing will happen in the next one. So if you see, this metal will take away SO4, you're left with H2O water and ammonia gas comes out. And you can see the other two examples right here. Now let's move on to the next is the lab preparation. So as I mentioned, you have two different lab preparations. This is the first one. The diagram for this lab preparation is on the third screen. When you download the notes, you'll find it on the third screen. So let's look at the equation. So NH4Cl reacting with your slaked lime. So if you see, this is the first reaction from the general preparation. You'll get CaCl2 plus water plus ammonia gas. And in this case, your alkali is present in axis. What is the precaution for this? So the flask is tilted in such a way that water formed in the reaction does not trickle down back into the heated flask and thus break it. So what is happening in this case, when I'll show you the diagram at the end of it, you will see that the flask in which your ammonia gas is going out with is tilted. The reason for that is the water doesn't trickle back down into the flask and break it. The next is the drying of ammonia. So ammonia is dried by passing it through a drying tower which contains pieces or lumps of quick lime, that is CaO. Now, why is ammonia not collected over other drying agents that could be concentrated H2SO4? So why does that happen? The reason is that ammonia is basic in nature and all other examples that we take are acidic in nature, and ammonia ends up reacting with them to give salt and water instead of getting dried by them. Now let's look at the collection of the gas. This particular gas is collected by downward displacement of air because it is lighter than air. The second is it is highly soluble in water, so we cannot collect it over water. So let's quickly read through the points. Drying of ammonia, passed through drying tower containing lumps of quick lime. Then collection, it is collected by downward displacement of air because it is lighter than air. Second, it is highly soluble in water, therefore cannot be collected over water. Other drying agents are not used because ammonia is basic in nature and will react with them. Let's look at the second part. Now, this is continued. The same lab preparation is continued in this one. Higher ratio by weight of alkali is used. It may counteract the loss of sublimation of NH4Cl. That's the first point. The second is CaOH whole twice, that is slaked lime, is used because it is cheap and not deliquescent like other alkalis. What is being deliquescent? That means ability to turn into vapors and mix with the atmosphere. So CaOH is not deliquescent. That is the reason we prefer this. The next is, though all ammonium salts on heating gives ammonia, yet NH4NO3 is explosive. Make sure that you remember that. And NH4NO2 on warming with alkalis do not produce ammonia because they decompose on heating. So let's look at these examples. NH4NO3 on heating will give you N2O plus water, and NH4NO2 on heating will give you nitrogen plus water. So instead of giving you ammonia as an output, they will end up decomposing themselves instead of giving you the required product. So these two are the exceptions that you need to remember. Let's move to the next part. This is your second lab preparation. So in this lab preparation, you have Mg, that is magnesium nitrate, and aluminium nitrate. So Mg3N2, and these reactions are with warm water. You have to remember this. And another thing that you have to remember is that this particular lab preparation is costly. So if asked in the exam which of the lab preparations would you prefer or which is more feasible, then the first one that we talked about is more feasible. Now let's look at this. So you have magnesium nitrate reacting with warm water, giving you magnesium hydroxide plus ammonia. And same thing is happening in the second one. You get aluminium hydroxide plus ammonia. Magnesium hydroxide or aluminium hydroxide are formed, but they remain in the flask and the ammonia gas escapes. So if you look at this diagram right here, so you have magnesium nitrate here. Your magnesium hydroxide is formed, but it stays in the flask. What goes out is only ammonia gas. Then you have the drying agent right here, and the ammonia gas is collected over here. Okay. Now, collection and drying is the same as the previous experiment that we did. Let's move to the next part, that is aqueous solution of ammonia. So what is aqueous solution of ammonia? When you have ammonia gas, you dissolve it in water, you get aqueous solution of ammonia. So NH3 plus water gives you ammonium hydroxide. So this is your aqueous solution of ammonia. Okay. So first equation is just making the aqueous solution. Ammonia in water give you ammonium hydroxide. Now, all other reactions after this are reactions of aqueous ammonia with acids and aqueous ammonia with metallic salts. Okay, let's start with the acids. So ammonium hydroxide reacting with HCl, HNO3 and H2SO4. These are the three reactions with acids. So when ammonium hydroxide is reacting with HCl, you will end up getting a salt plus water. So NH4Cl, NH4NO3 and ammonium hydroxide plus water. Very simple. The next ones that you see right here are from analytical chemistry. That is, you have different salts: iron sulfate, iron chloride, lead nitrate, zinc nitrate and copper. They are reacting with ammonium hydroxide and you are getting salt plus a precipitate, a PPT. So FeOH whole twice is a dirty green PPT. FeOH whole thrice is a reddish brown PPT. Lead hydroxide is white. Zinc hydroxide is gelatinous white, and copper hydroxide is pale blue in color. If you have any confusion about understanding the analytical chemistry and learning these precipitates, please go ahead and check out the channel. I have mentioned the easiest way ever to learn these precipitates, color and identify anions, cations, all of them. So make sure that you check out that video on the channel. Now let's move ahead to the catalytic oxidation of ammonia. So what is happening in this case is ammonia is reacting with oxygen in the presence of platinum at 800 degrees Celsius, giving you water, NO and heat. This NO, that is nitric oxide, this reacts with oxygen to give you NO2, that is nitrogen dioxide, which is a brown gas. Okay. So what is the observation here? The observation is reddish brown gas vapors of nitrogen dioxide are seen in the flask due to the oxidation of nitric oxide. And the second observation is that platinum continues to glow even after the heat is discontinued, because this is an exothermic reaction. So still there will be sufficient heat for the catalyst to keep getting heat and show some glow in it. So let's look at the diagram. You have dry oxygen coming in from here, dry ammonia coming in from here, platinum as a catalyst is right here, and you're providing it heat. Now some water droplets are present, and then eventually you see NO2 over here, which is a reddish brown fume. Okay, so that confirms nitrogen dioxide. Let's move to the next one. So you have fountain experiment. Fountain experiment is same fountain experiment like you did for HCl gas. The only difference is that instead of using blue litmus solution in the water trough, you will use red litmus solution, and the fountain will be blue in color because this particular gas is basic in nature. So let's read it quickly. To demonstrate high solubility of ammonia gas, so what we are trying is, you have a round bottom flask on top and you have a red litmus solution right here. As soon as you press this dropper, some water will go into the round bottomed flask and few drops of water is able to dissolve in a lot of ammonia. And when that happens, vacuum is created in the round bottom flask, which makes the water from the water trough to rush up through the tube. And as soon as it reaches the round bottom flask, the left out ammonia in that will quickly turn your red litmus solution to blue because it is basic in nature, and you can see a blue fountain in the round bottom flask. Now let's quickly read the theory here. Okay, I hope it is visible now. As few drops of water enter the flask, ammonia gas present in the flask gets dissolved in water due to high solubility. This creates a partial vacuum in the flask. Since outside pressure is higher, the red litmus solution rushes up through the jet tube and emerges as a blue fountain. Ammonia gas, being basic, changes red litmus solution to blue. Let's move ahead to the next part, that is burning of ammonia in oxygen. So ammonia is not a supporter of combustion. It extinguishes a burning splint and does not burn in air. It burns in oxygen with greenish yellow flame. That is NH3 plus oxygen is giving you nitrogen plus water. This reaction is irreversible and strongly exothermic. Mixture of ammonia and oxygen is explosive and dangerous. So if you look at this particular experiment, you have dry ammonia gas entering from right here and you have pure oxygen coming in. And this particular flame that you can see is a greenish yellow flame that burns, that happens because ammonia is burning in pure oxygen. Okay, so I hope this is clear to you. So this is the first screen that we have covered. Let's quickly move to the next one. The next is, let's start with it. So ammonia has a sharp characteristic odor. Then second, it turns moist red litmus blue and moist turmeric paper brown. It turns phenolphthalein solution pink. So these are some characteristic properties of ammonia. Let's start with Haber's process. So Haber's process is an industrial manufacturing of ammonia gas. And so let's start with the first part, that is nitrogen and hydrogen is used in the ratio of 1:3 by volume. Nitrogen is obtained by fractional distillation of liquid air. They can ask you a question, how are the reactants produced, or what is the source of the reactants used for Haber's process. So that was for nitrogen. For hydrogen, we get it from water gas, that is the Bosch process or natural gas. What is the reaction? Nitrogen combining with hydrogen giving you ammonia plus heat. This means it's an exothermic reaction. So the reaction is reversible, exothermic, and proceeds with a decrease in volume. Okay. What are the favorable conditions? Very important, students, mark this important. Temperature is 450 to 500 degrees Celsius. Pressure is above 200 atm. Catalyst is finely divided iron. Promoter is traces of molybdenum or aluminium oxide. Let's move to the second part of Haber's process, rate of conversion. So about 15% of reacting gases gets converted to ammonia. So what happens is whatever reactants are coming in, you get 15% of ammonia out of it, and other gases, whatever is left out, is sent back into the reaction. So this process continues, and at the end you are able to get about 98% of ammonia. Now, recovery of ammonia. So when the reaction happens and at the end you get ammonia gas, all three gases are mixed together. So how are you getting ammonia out of it? So that is liquefaction. Why? Because hydrogen and nitrogen is not easily liquefied. So when you try and put in more pressure and you try to liquefy it, ammonia is easily able to come out. The second is absorbing in water, because ammonia is highly soluble in water, whereas hydrogen and nitrogen are not. Now let's look at the process of Haber's quickly on the screen. So dry nitrogen and hydrogen are entering from here. Then if you see, there is a compression pump. So in the compression pump, your dry gases are coming in. You put extra pressure on the gases, and then you send it further into the electrically heated catalytic chamber. So dry gases are coming in, pressurize it with extra pressure, throw them into the electrically heated catalytic chamber. What catalysts are present here? You have finely divided iron, molybdenum, or you have aluminium oxide present here. So over here your reaction happens. Once this reaction happens, it is highly exothermic. So the gases that are coming out are very hot. These hot gases are pushed into the condenser or cooling pipes. Over here, your entire temperature comes down further. Now this is where your 15% of ammonia is left out. So 15% of ammonia comes out as liquid ammonia. You liquefy it right after. 15% of ammonia comes out. Whatever is left out goes back into the compression pump. So nitrogen and hydrogen left out will go back into the compression pump. You can look at the reaction right here. All the conditions are mentioned. So 450 to 500 degrees Celsius, above 200 atm, N2 plus hydrogen gives you NH3 plus heat. So this is your basic understanding of Haber's process. Now let's look at the notes. The first is the reaction is exothermic, hence low temperature will favor the synthesis. However, at low temperature the reaction proceeds slowly. Okay. Now 4 volumes of reactants produce 2 volumes of ammonia. Hence, high pressure favors the formation of ammonia. That is the reason in the beginning in compression pump, you are trying to put in more pressure and then put it forward. So what is the favorable atmospheric pressure for this? It is 200 atm. The next is, since the reaction is exothermic, the heat evolved further, maintains the temperature. External heating is not required after the reactants are heated initially. Therefore, the temperature that you need here is 450 to 500 degrees Celsius. Okay. The next is the purification of nitrogen and hydrogen is very necessary because it may contain impurities. What kind of impurities? It may contain carbon dioxide, carbon monoxide, or some traces of sulfur. If these type of things are present, they can end up poisoning the catalyst. And if the catalyst gets poisoned, of course, the entire process becomes very slow and inefficient. Therefore, it's important that nitrogen and hydrogen are properly purified before entering the entire process. Now, this is your diagram for Haber's process. You can take a look at this, and if you have doubts, you can ask that in the comment section. Now, let's move ahead to the, let's come on this side. That is ammonia as a reducing agent. So in this case, what is happening? Reduction of metallic oxides. So if you have a metallic oxide, ammonia gas reduces it and you get metal, water, and along with that nitrogen gas. So let's look at that. So you have ammonia reacting with copper oxide. This copper oxide is red hot copper oxide, which is black in color, black solid. You get a reddish brown copper plus water plus nitrogen gas. Same thing is happening in lead oxide. You have PbO plus ammonia. You get lead plus water plus nitrogen gas. Your lead oxide was yellow in color. Lead is grayish in color. Let's look at the diagram. So you have dry ammonia coming in. Over here, you'll either have copper oxide or lead oxide depending on what is happening in the reaction. You have copper oxide mentioned here. You provided heat. So when you provided heat, it turns into proper copper and nitrogen gas goes further. So if you see copper, water, cold, so you have cold water present here. This portion, okay, when you see there's a line and there are certain dots. What happens in this case is that water vapor that are coming along with nitrogen, they will condense and settle down, whereas nitrogen gas will further move ahead. So when nitrogen gas further moves ahead, it is collected right here. Okay, now let's look at this. The water formed is collected in U tube and is tested with anhydrous copper sulfate, turns blue. So how do you test water? You can take anhydrous copper sulfate and it turns blue in the presence of water. Therefore, this shows that ammonia is made up of nitrogen and hydrogen. Okay, let's move to the next one. This is still ammonia as a reducing agent. In this case, reduction of chlorine to hydrogen chloride. Okay, so we are reducing chlorine to hydrogen chloride. Reduction of when ammonia is in excess. So when ammonia is in excess, what happens? You have ammonia plus chlorine giving you nitrogen plus ammonium chloride. Yellow green color of chlorine disappears. So what happens is, initially you have the reaction happening with chlorine and this HCl goes further and reacts with leftover ammonia. So the chlorine gas that you initially had in the reaction, that turns, that changes. So yellowish green color of chlorine disappears and white fumes of ammonium chloride are formed. The next is when chlorine is in excess. So ammonia plus chlorine will give you HCl plus NCl3. When chlorine is in excess, you get NCl3, which is highly explosive nitrogen trichloride. What does this entire reaction show? This shows that chlorine has high affinity for nitrogen, and second, ammonia is a reducing agent. So it works as an example for both of the things. So I hope this is clear. Let's move ahead to the last portion, that is chemical properties. I think we have one more. Okay, let's start with chemical properties, that is reaction with acids. When ammonia gas reacts with HCl gas, it gives you NH4Cl. When ammonia gas reacts with HNO3, it gives you NH4NO3, and the same thing you'll have for H2SO4. Ammonium nitrate and ammonium chloride both show thermal dissociation, that is NH4Cl and NH4NO3 on providing heat gives you ammonia plus HCl. The second case will give you N2O plus water. It thermally dissociates. Let's look at the last portion, that is tests for ammonia. So the first test is common for HCl and ammonia, that is NH3 plus HCl gives you NH4Cl, that is dense white fumes of ammonium chloride. When ammonia is passed through CuSO4, it gives you a blue PPT which changes into deep blue on passing excess gas into it. So when you add more ammonia to it, it changes into a deep blue solution. So copper sulfate will give you a PPT blue in color, and when you keep passing more ammonia to it, it turns into a deep blue solution. The next is, all ammonium salts generally produce ammonia gas when warmed with alkali like sodium hydroxides. Now, if you come on the last page, this is the preparation that we started with, the first lab preparation. This particular jar is tilted, so your ammonia gas goes out, and whatever water is there, it does not trickle back into the reactants. Even if there is water, it will come along with it as water vapor, and then you have a drying agent which will absorb all the moisture and water vapor. Okay, so this is the lab preparation for dry ammonia. So my dear students, this was it for today's session. I hope it definitely helped you out, and whatever I'm trying to do, that means trying to keep the videos short and crisp and not waste a lot of time during your examination and help you revise through. I hope it helps you out, and make sure that you are thoroughly revising your syllabus. Do not be scared. If there is any portion in chemistry that I can help you out with, make sure that you reach out to me, and I'll try my best to address all of the concerns. Thank you so much. Download the notes from the description box or the Telegram channel, and I hope you have a wonderful day ahead. Thank you so much.